Hey, what's up guys? Welcome back to the channel. So today's video is about the heap sort. No doubt very important concept guys, and frequently asked by companies like Amazon, Microsoft, Flipkart and many more. So I want you guys to stay tuned till the end of the video, because in this video I'm going to cover everything you need to know about heap sort. Whether it's the introduction to heap sort, the basic fundamentals behind heap sort, algorithm, pseudocode, complexity analysis and the code in C++, Java and Python. So without any further delay, let's get started. Okay, so I have written the introduction here guys, and it says that heap sort is basically a comparison based sorting algorithm. Heap sort can be thought of as an improved selection sort. Now at this point guys, I want you to recall the basic idea behind the heap sort. First of all, let me draw an array. So let's say I have a sorted array which contains element 1, 2, 3, 4, 5, 6. Now in this array guys, notice one thing, that every smaller element is present on the left side and every greater element is present on the right side, right? Okay, this is about the ascending order of element guys. Now I have written a pseudocode for selection sort here. See, I am going to start from the left position, then every time I look for the smaller element on the right side and then I swap this element with the current index, so that every smaller element gets to the left side, right? So see, for this 5, I'm going to traverse all the elements in this part and I'm going to find the smaller element, right? So this is the smallest element, and now I'm going to move this element to the leftmost position. So you can see that I have got 1 here, right? And 1 is now at its current position, you can see here. Okay, now my I will move here, right? Initially the I was at 0 position, now the I is at first position. So I am going to look for the smallest element in this area, and this is the smallest element, right? So just swap this element with this 7. So this way I am able to get these two elements at their current position. So you can see that initially this was the unsorted part, right? After this is the unsorted part, then this is the unsorted part. So unsorted part is going to shrink every time and the sorted part is going to expand, right? So this is the basic idea behind the selection sort. Now one question that you may ask me is, hey, can we implement the selection sort by starting from the right and each time moving the maximum element to the rightmost places, right? So yes, of course we can do this. In this particular approach, the concept is going to remain same, right? Because it's the selection sort. We have to select either the greater or the smaller element based on the type of implementation. So see, when we talk about like looking for the maximum element, then we have to start from the right position because we want the maximum element to the right position, right? So I'll say that, okay, my I will start from n minus 1, then I is greater than equal to 0, then I minus minus, right? So this is the loop that we have, and inside this loop I have to get the max element, right? So I'll get the max element. So let's say at any point in time, okay, so let me write the array first. I have 5 7 1 4 3. This is the initial array, right? And I'm currently at this index. So see, I have to look for the greatest element in this area, and once I have seen the greatest element, which is 7 here for this case, so I'll swap this element with the current ith position, right? So see, I'll write index equal to get max index from 0 to I minus 1, right? So I'll write, instead of this, I'll write from 0 to I minus 1, and I'll change this condition as well. If my this index is even greater than the ith position, then I'll simply swap them. This way I'll be able to get max element to the rightmost position every time. And see, this is the output that we'll get. First we'll get 7 here, then we will get 5 here, then 4 here, then 3 here, then 1, right? So this is the basic idea behind this selection sort, right? Now talking about the time complexity, because this is something from this point we are going to start building the idea behind the heap sort. See, the complexity of this code is O of n for outer loop, then O of n for inner loop, right? Because we are going to traverse every element in order to get the max element. Okay, so the total complexity this way will be O of n square, and this is the complexity for selection sort, right? We have already seen that. Okay, now the question is, can we optimize this complexity? So see, we are getting like maximum element each time by traversing the array, right? Which is causing O of n complexity. But we can do the same in O of log n, and this is something which gives us a basic idea behind the heap sort, right? So heap sort is basically an optimization of selection sort, where we use a binary heap data structure to find the maximum element in an effective way, right? So once we have optimized this particular method, then the complexity will reduce to O of n log n. So this is how the idea of heap sort comes to our mind, right? Now let's talk about what exactly is a binary heap data structure, because this is something which is giving us the maximum element in an optimal manner, right? So I'm really curious to know about this binary heap data structure. So let's start with binary heap. Okay, so I have written the definition of binary heap here, right? And it's saying that binary heap is a complete binary tree which is used to store data efficiently to get the max or min based on its structure, right? A binary heap can be a max heap or min heap. It's obvious, right? We can like have both type of implementation where a binary heap is going to give us the maximum element or the minimum element, right? So now I want to give you an example of binary heap. So see, binary heap is a complete binary tree, right? Okay, which is used to store data efficiently. So let me show you how a binary heap store data. So binary heap is a complete binary tree. So a complete binary tree is a binary tree where we have every level filled, most probably the last level where each element or each node is as left as possible. So this is the example of a complete binary tree, right? We have every level which is a complete level, right? And for the last level it's not completely filled, we have every element as left as possible. So let me write the element as well. Let's say I have 6 here, then I have 2 here, 4 here, then I have 1 here and 0 here. This is the example of a binary heap. See, root element is always greater than all other elements, right? And even if you take any of the subtrees, let's say this subtree, so for this subtree as well you can see that the root element is greater than the children element, right? And for this the root element is again greater than every element below this, below the hierarchy. So this is what a binary heap is. I have written one example, there can be many examples. So this is basically the example of a max heap, right? We can similarly we can have the example of min heap as well. So let's say I have uh, 0 here, then I have 1 here, then I have 2 here, right? After this 3, then 4, then 5, then 6. So this is the example of min heap. See, we have the root which is pointing to the minimum element, right? So this is what the binary heap is. Now we are going to talk about how we can convert an array to a binary heap, right? Because see, in the heap sort we are given an array and we have to use a binary heap data structure. So we have to convert this array to a binary heap, right? So how we convert an array to a binary heap, let's discuss it. Okay, so I have written one array as an example, and I'm going to convert this particular array into a binary max heap, right? Okay, so let me write max here. This is a binary max heap. Fine. So now we know what exactly is a binary heap. So a binary heap is basically a complete binary tree which certain set of conditions, right? So first task is to convert this array into a complete binary tree. So how to convert? Let me explain. First of all, I am going to write the structure of a complete binary tree. So this is how the structure looks like, right? Isn't it? So this is basically the structure of complete binary tree. I think that's enough, these much of notes. So see, we always have every level which is a completely filled level, most probably the last level where the nodes are as left as possible. So this is what the definition of complete binary tree is. Now the task is to iterate over each element from left to right and then write these element in a binary tree from left to right manner in each level, right? So I'll come to 5 first, then I'll write 5 here, after this 6, so 6 here, then 2, so write 2 here, after this 7, so I'll write 7 here, then 3, 3 here, after this 0, right? So this is how I can fill the elements. Let me remove all other nodes. So this is how I can convert any array representation to a complete binary tree, right? One important thing to remember about array representation is the left child is always present at index 2 cross I plus 1 for any node I, right? So let's say this is node I, then the left child will be at 2 cross I plus 1. For this the index is 2, so 2 cross like 2 plus 1, which is nothing but 5, right? So 5 is this index. This means that the left child of 2 is always 0. Okay, similarly the right child is present at 2 cross I plus 2. So these are the things that are very important about the array representation, guys, right? Now as I have written the array represent okay, now I have written the tree representation of this array. So let's start converting this array into a binary max heap, right? For any binary max heap, we know that the root value is always greater than like these values, right, children? So this S is representing smaller values and G is representing greater values. So I'm going to check this particular condition for every node. I'll start with this node. This node doesn't have any children, right? So don't need to check for this node. Again, for this and this, don't need to check for these nodes, which are the leaves node, right? So this is the first node or first parent node which has at least one child, right? So you can see that it has only one child, and the child value is something which is smaller than the like node value. So this particular part is following the binary max heap property. What about this one? So for this node you can see that the node value is something which is smaller than the value of this left child. So this is not following. So in that case I need to swap these value. Once I swap these value, so I'll get the new structure, which is 5 here, then 7 here, 2 and 0 are going to remain same. After this I'll get 6 here, then 3 here, right? So I'm done with this particular node as well. So now this node is following the binary heap, binary max heap property. Now I'll come to the last node, which is this 5, right? So for this 5, again I'm going to check the children's. So you can see that left child is having the greater value. So again swap the values. This way I will have 7 for the root node. Then I'll have 5, 2, like all the smaller values on the children's, right? Okay. Now there is one more thing, that once I swap these values, then this structure gets ruined, right? So I have to again check for this particular thing, because you can see that now 6 is greater. So I'll write 5 here and 6 here. So this is the complete binary max heap that we have got out of this array, right? So this is how we convert. Now the question is, can we write the code out of this? So of course we can write the code. Now I'm going to write the code. Okay, so let me remove this particular step as well, and I want you guys to note down this particular thing, or let me write it somewhere. So let me write it here. I'll write left child is present at 2 cross I plus 1 and right child is present at 2 cross I plus 2, right? Okay, so now let me write the code in this particular area. See how the code looks like. I'm checking for each node, and what condition I'm checking. So this is basically the root value should be greater than the value of children nodes, right? So I'm checking for each node, so I'll write for I equals to n minus 1, then I is greater than equal to 0, then I minus minus. Why I am moving from behinds? Because you can see that the moment I start from leaf node, so first 0, then 3, then 7, this is how I'm checking. 0, 3, 7, then 2, then like 6, 5. So this is right to left order, right? So inside this particular loop, I have to check, okay, let me write check function here. So this function is going to check this particular condition for every node, right? So how to write? I'm simply going to pass array, then n, then I. So this is a kind of function, right? And even let me name this whole function as a build heap function. So this is build heap. This function is going to build heap, right? And this is going to take two parameters, array and n. So this is a function which is a build heap function, right? And what about this check function? Okay, so before talking about the check function, I want to talk about this particular like this particular thing. See, when we checked for 0 and 3 and like 7, so you can notice one thing, that these node doesn't have any like children, and even it's obvious because these are leaves node, and leaves node doesn't have any children, right? So any tree can have leaves node. So we have to make sure that we don't check leaves node, because it's like of no use, right? So I have to start from the first parent, and always remember guys, in like array representation of tree, the first parent is always present at the index n by 2 minus 1, where n is basically the size of this array, right? And we can derive this relation as well, but for this video I'm not going to derive, because this is something which is out of this video. So I'm directly going to write n by 2 minus 1 here, right? So this is the point from where I have to start, then I'm going to move till the index 0, right? So even you can see here, if 1 2 3 4 5 6, like 6 is the size, then 6 by 2 is 3, 3 minus 1 is 2. So I'm starting from index 2, right? And then I'm checking 2 6 5. So 2 6 5 are the values that I'm actually checking. I'm not checking these three values. So this is about the build heap function. And now I will talk about the check function. And even instead of writing this check, let me write heapify here, because this function is most popularly known as heapify function, right? Because this is going to heapify each node. Now let's talk about the heapify function in detail, right? Okay, so I think I have to write the same example first, right? So see, what is the example? The example is 562 then 730. Okay, 562 then 730. So I'll write heapify function. Let's say I have a function which is heapify. See what parameters this function was taking. So first array, then we have n, then we have I, right? Because I have to check for current node. So see here, I'm passing these three values, because let's say I is the current children, so I have to check for current children, like the value of children should be smaller than the root value, right? Okay, so this is the function. Now see, let me draw this tree again. So I have 5, then I have 6, then I have 2, then 7, then 3, then 0, right? So let's say I'm checking for this node. So you can see here that I'm checking this particular value with left and right child. So first of all, get the left and right child. How to get? So I have already explained this. This is how I can get the index of left and right child. So I'm going to write here, right? Let me write here left child is equal to 2 cross I plus 1, and I is something that comes from here, right? And right child is equal to 2 cross I plus 2, right? And for now, let's assume that the largest value is equal to at I index, right? So largest value is at this root index. So I will check if my like array of left is something which is greater than uh, array of largest. So in that case, I can say that, okay, my assumption was wrong and the greatest element is this particular like left child, right? So I can say that, okay, now my largest is equal to left child. But see, there is one more thing that I need to check before I check this condition. This left can be out of index as well. Let's say for this particular like element, we don't have any left child, right? For this 7, we don't have any left child. So this is something which is going to give us an error. So I have to handle this case. If my left is smaller than n and this condition is true, right? Similarly, I have to check for right as well. So I'll check if my right is smaller than n and my array of right is something which is greater than array of largest. So this way I can again say that my assumption was wrong and the right child is the largest. So I'll say that largest equal to right, right? So at last I will be able to get the largest element, right? Okay, so now all I will do is I'll say that, okay, see, for this particular case, I have this as the current largest, like initial largest element, which is I, and this is my new largest element. So you can see that this is my new largest element, because when these conditions become true, so largest will be assigned to left. So okay, now my largest is pointing to this particular child. So I'll simply say that if my largest variable is not equal to I, this means that the largest is not the root element. So I have to swap some elements. Which elements I need to swap? I need to swap uh, array of I and array of largest, right? So I'll write swap array of I and then array of largest. Make sense till now? This way I will be able to get this 7 here and this 6 here, right? So the new heap is 5, then 7, then 2, 0, then I have 6 here, then I have 3 here. Make sense till now? So this is how we can get, right? Once I am done with this, then I'll come to this point and again I'll check the conditions, right? And I'll swap these two values. So what I'll have is, after this I'll have 5 here and 7 here. So I can say that I have got my heap, right? Is it right? So it is wrong, right? Because although I have the maximum element at the root position, but this is not again following the condition, right? So once I swap these two values, then I have to make sure that the largest is again heapified. So I'll call the same function for the largest, because this is something which is the largest for this case, right? So I'll call the same function heapify for the largest, right? So I'll say that, okay, array comma n comma largest is the child which I'm modifying. So this is what the complete heapify function looks like, right? And heapify along with this build heap function can give me any array converted to heap, right? So okay, now if I want to convert the array to heap, then I can simply convert. So this is about the binary heap like working. Now let's talk about the heap sort algorithm in detail. See, I have this array, right? So what I'll do is I'll first convert this array into a heap. So once I convert the array into heap, then I have to call the build heap function, right? So I'll say that, okay, build heap out of the given array. So I'll have the heap, and let me put this thing into a function. So let's say I have a heap sort function, heap sort, and this function is basically going to take array as the parameter and n, right? So this is the heap sort function. Okay, now once I have built the heap, then this is the heap that we have, which is containing elements 7, then 6, then 2, then 5, 3, 0. So let me write it here. I have converted heap is 7, then 6, then 2, then 5, 3, 0, right? Okay, so see, now you can see that I have got the maximum element on the array of 0th position, right? So what I'll do is I'll start with this position and I'll say that at this position, this is storing the maximum value, so I'll simply swap array of I and array of 0. Makes sense, right? So what I'll do is I'll say that okay, for I equals to n minus 1, then I is greater than equal to 0. I is greater than 0, then I minus minus. There is no need to write equal to even, right? So inside this, what I'll do is I'll say that my array of 0 is storing the maximum element because I have got build heap, right? So I'll say that okay, swap array of 0 and array of I, right? So once I do this, then I will have this 7 here. I'll have this 7 here and 0 here. So my new like state of the array is 0 here, then 6, then 2, then 5, then 3, then 7. So I can say that this 7 is at current position, right? And now I have to again convert this particular heap into a this particular array into a heap, right? Because this is not heap right now. See, initial heap was 7, then 6, then 2, then 0 here, then 5 here, then 3 here, right? And I have swapped these two values. My 0 is here and my 7 is here. So you can see that my 0 is here. This means that this is not a heap now. So see, these values are already following the property. So I just need to call the heapify function for this particular place. So I'll say that okay, called heapify function for array and 0 child, right? And what is the size of the array? Now the size of array is going to shrink. So initially the size of array was from 0 to n minus 1, right? So or 0 to I, my I will decrease. So I'll say that okay, now my size is from 0 to I, right? So this is the size. So I'll say that okay, now my new size is I. So this way I can get every greater element on the right side, right? And this is how my unsorted area is going to shrink every time. So isn't it similar to the selection sort technique? The only difference is these two steps are able to give me the maximum element in just O of log n, right? So this is how the heap sort algorithm works, right? Now see, this is the heap sort function. After this, see, it is using build heap function, then build heap and heapify. So I have already explained you how the heapify function work and build heap function work. So I think this is all about the heap sort. The only thing that we are left with is time complexity, and even I have explained the time complexity also in detail how it works. See, we are getting the maximum element in just O of log n, and after this we are getting like this loop is running O of n, so the total complexity is O of n log n. And what about the space complexity? So we are not using any extra space apart from just that recursion space, right, which is O of log n. Why log n? Because whenever we have n nodes then and we form a tree, so the tree size have log n, right? So that's why the space complexity becomes log n when we call the function heapify recursively. So I think this is all about this video. So let me quickly show you the code, guys. This is the code. See, I have written the C++ code on the left hand side. You can see that I have the heapify function first, very similar to the one I have explained you. I have build heap function for, after this. Then at last I have the heap sort function, right? And I think once you have understood the problem, once you have understood the concept well, then everything will be clear to you why I'm using build heap, why I'm using n by 2 minus 1. So this is the Java code, right? On the right hand side I have written the Java code, and then I have written the Python code, and I'm even going to provide this code link into the description box. So guys, make sure you check out the description as well. This is all about this video, guys. If you like the explanation, then hit the like button, and if you are new here, then subscribe the channel. Thank you.